Hi, my name is Stephanie Heron, and I'm going to be doing a video on mass and IR spectroscopy. So first, mass spectroscopy. There are three basic steps. The first step is ionization. This occurs whenever a small sample loses an electron. Next, in analysis, the ions are sorted and separated according to charge and mass. In detection, the separated ions are organized into a chart, which is what we see whenever we look at a mass spectroscopy spectra. So the purpose of mass spectroscopy is to analyze molecules and patterns according to mass. It does this using fragmentation, which is the pattern formed from the dissociation of energetically unstable ions. And there's a few distinctive atoms that you can look for whenever you're analyzing a spectra. Chlorine, which occurs in a 3:1 peak ratio, and bromine, which occurs in a 1:1 peak ratio. So to discover the chemical compound shown here, 5 things must be determined. First, the M+ value. This is the rightmost value on the spectra, and it also reveals the molar mass. So here we have about 107. So the compound, that's going to be its total molecular mass. Then we have the base peak, and this is the highest peak on the chart to the left. So here we can see it's about at 77. Next, determining the formula is a little bit harder, but you use some simple math. So we start with the molar mass, which was also the M+ value. And if your M+ value is negative, as ours is, then we know that the compound contains nitrogen, so that's a pretty good place to start. So we will subtract the molar mass of one nitrogen atom, and that will give us 93. So then we go ahead and subtract the molar mass of 7 carbon atoms, because that's the most. 12 will go into 93 7 times, and then we're left over with 9, and that leaves us with 9 hydrogens. So we have 1 nitrogen, 7 carbons, 9 hydrogens, which gives us our formula C7H9. Next, we look for degrees of unsaturation, and that tells us how many rings and double bonds we are dealing with. And here is the equation below. So I plugged in the number of carbons, nitrogens, and hydrogens, and I ended up with 4. This means that we have 1 ring and 3 pi bonds. So that enables us to predict the structure. Here's our ring, here's our nitrogen, here's our double bonds, and here's our methyl groups. Next, we're going to analyze IR spectroscopy. The point of this is to specify the presence and location of functional groups in a compound. So here we're looking for large peaks and in which zone they occur. The more polar, the stronger the peak. So there's 5 to 6 zones depending on what you're analyzing. The first 5 zones are always analyzed. Sometimes a fingerprint region is used, but for this video we won't worry about it. So there's the ranges of all the zones. And here's a really helpful handout from Compound Chem, and it basically tells you what zones everything is in and what exactly you're looking for. So if you have a really low peak right here, you'll know you'll have a carboxylic acid and so on. It's really helpful. So that is what was used to analyze the IR spectra. So here's the IR spectroscopy of the same compound we just looked at the mass spec of. And looking here, we can see there's a really low peak, around 1500. So that tells us that it's a nitro compound. So we knew we had nitrogen already, but that does help us. Next, we go to look at this peak, and that tells us that we have an aromatic ring. So we know we have an aromatic ring, we know we have nitrogen, and we know we have some extra hydrogens that need to be added to the compound. So using that information, we can come up with this compound. Once again, we have our benzene ring, we have our nitrogen, and we have our 2 methyl groups coming off the side, which creates dimethyl pyridine.